Welcome everyone. Good day to you all, and welcome to today's webinar. We'll see how Medium re-architected its feature store for low latency at scale. This is really an in-depth look into how Medium changed its architecture in order to achieve extremely low latency at a very large scale for the website using ScyllaDB. So welcome everyone. Later on, we'll have Andréas Saudemont, which is a Medium software engineer, and he'll be presenting his story for us all today. So a little bit about me before we start. I'm a technical director at ScyllaDB. I previously worked as a solutions architect in many industries, such as publishing, such as mediums, streaming, and automotive industries as well. So I have a very extensive background in ScyllaDB. ScyllaDB, for those who are not very familiar with it, is a predictable performance at scale database that focuses on monstrous scale at a massive speed and massive scale. And we're industry leading price performance in terms of usually bringing low latency, so single digits millisecond, really close to the hardware architecture, delivering that really fast speed database queries for every multiple different workloads at NoSQL scale, being predictably low at P99s as well. High throughput usually means that we'll sustain millions of operations per second, including being within the low latency targets that offer single digits millisecond on P99 latency as well. And at global scale, our major customers run at multiple data centers, multiple regions across the globe, really distributed the workload, being closer to their users and providing really fast response time, extremely low latency for local requests, while being able to serve requests on a global scale with a high consistency and extreme performance. The ScyllaDB, as we call it, sweet spot, is the typical teams that are using ScyllaDB and being very successful with it. So on the x-axis, we do have databases that have a lower latency target, and the y-axis, the vertical one, we see operations per second, meaning that as our users aggregate towards being in hundreds of thousands, if not millions of operations per second at extremely low latency targets, usually single digits millisecond for P99, as we initially discussed, especially for those use cases that are already in the high ratio and the high spot, but they're still expected to grow. So those use cases can really scale very nicely with Scylla, as Scylla linearly scale for targeting those ever-changing and ever-growing workloads. The upside of Scylla is that you actually have to babysit the database. ScyllaDB is a very autonomous database and works really flawlessly without being actually handled on a day-to-day basis by DBAs or any sort of additional professionals that need to be working directly with it. As developers, as Andréas will present, it's just a set and use and be really efficient with the usage as well. Some of the major game changers that leverage ScyllaDB, Comcast usually provides powering over 50 million DVR devices with 1 billion requests per day. Those use cases are really migrating from databases that can't reach a single digit millisecond latency targets and being very effective in running Scylla. TripAdvisor also provides a real-time machine learning-driven recommendation platform that leverages ScyllaDB for its own its millions of users per day. And Caesars Entertainment is usually targeting low latency global sports, betting within those parameters as well. So usually efficiently using ScyllaDB to cover multiple applications and multiple games across their dashboards. Today, I have with me Andréas Saudemont, which is a principal software engineer at Medium, and I'll let him to share his story. Andréas?
Yes, thanks, B. Hi, everyone. Super happy to be there. So my name is Andréas Saudemont. I'm a principal software engineer at Medium, been there almost 5 years now. I'm working on various things at Medium, but one of my favorite topics is to work on our scalable architectures that support the heavy load that Medium has to support. So what are we going to talk about today? we will first go over the feature store, what it is, what is its architecture, and how does it fit within the whole Medium architecture. We'll take a look at what we are calling features and a subtype of feature that we are calling relational features. Next, we'll go over the list features. That's the new kind of feature that we've been adding a few months ago in order to replace the relational features. We'll then look at how we designed the ScyllaDB data model for list features in a way that make them scalable and able to support the target load. Next, we'll go over the list operation, how we implemented them in order, once again, to be efficient. And we'll conclude with some metrics on these implementations. Okay, let's get started. So the feature store, what is it? The feature store is a key component of the recommendation system at Medium. It is used as input by the machine learning models that power various surfaces on Medium, and most specifically the For You feed and the daily digest. You can think of it as a specialized database with a specialized API that is able to support low latency and high throughput access patterns. So I mentioned the For You feed. What is it? That's the thing that you see when you open the Medium homepage when you're logged in. It provides a list of stories that we think you are likely to enjoy reading based on your reading history, based on the people you follow, based on the reading history of the people you follow, and stuff like that. The daily digest is also a set of recommendations that we're sending you once per day via email and also via the mobile apps. All of this is powered by the feature store. And let's now take a look at how we are architecting this. So this is a very simplified view of the Medium architecture, centered most specifically on the feature store. So in the center, you can see the feature store. This is one of the services that is run on the cloud for Medium. We do have a lot of services. And the input to the feature store is mostly user events. So whenever you view a story, whenever a story is presented to you, whenever you follow someone and things like that, that's a user event, and that's one input to the feature store. We also have some internal events, like when a post is published, when a post is spam scored, when we give a spam score to a post, and things like that. All of that comes as input into the feature store. This is stored as feature values, like we'll see later. And all of this is then used as input for the machine learning models and the various models that we have that power the recommendation surface, which are then used to show recommendations on the medium.com surface. So you can see there is a virtuous circle here. The things that you read provide input to the things that you'll read next, or that will recommend you to read next. Okay, let's talk a bit about features. This is the key of the feature store. What we call a feature is a property of an entity in a feature store. An entity can be just about anyone. Typically, it can be a user, a story. We do have also some very specialized entities. We won't go into them yet here. So one feature is defined by an entity type, an associated entity type, for instance, user or story, the name of the story. So for instance, that would be an isMember feature name, the data type of its values. We could say, for instance, a Boolean, but that can also be an integer, that can be a vector, that can be stuff like that. We do support optionally versions on features so that we can have, for instance, daily versions of features. That's super useful for historical training on data models, on machine learning models, sorry. And next, features do have values. One feature has a set of values, and a feature value is the value of a given feature for a given entity ID. So for instance, we could have the user.isMember feature for entity user123, which would be set to true. That would mean that the user with ID user123 is a member, a medium member. Okay, that's the feature. Now we do have a specialized kind of feature that we call relational features. That is used for cross-entity relationships. Like for instance, when you want to say that a given user has read a given story. So the specificity of a relational feature that it can have multiple values for a given entity ID. So each of these values is defined by a relation ID. So that's the ID of the related entity, and a timestamp corresponding to the timestamp of the event that is being stored in the value. So a sample relational feature would be story.user_has_read, which records the users who have read a given story. So it is attached to the story entity type. It relates with the user entity type, and its values indicate whether and when a given user has read a given story. Okay, that's a bit complex. Maybe let's take a look at a schema that hopefully makes it a bit simpler to understand. In the center, we have the concept of features and entity types. So as you can see, a feature is attached to an entity type. It also is defined via its feature name, its feature version, and its data type, just as we saw. An entity type is just an abstract concept, and it has a set of IDs, of associated IDs. At the top, we have the non-relational features. So that's defined by their associated feature, the entity ID, and the value. And at the bottom, we have relational features. So as you can see, it's also associated with a feature. It's associated with an entity ID, but it also has a relation ID, which maps to an entity type, an ID of an entity type. And in addition to that, a relational feature value has the value itself and a timestamp. Okay, hopefully this is clear. Relational features, unfortunately, have some serious limitations because they have been implemented with a suboptimal data model. In essence, the data for relational features is split across two tables, which means that when we want to fetch values for a given relational feature, it's very inefficient. First, we have to do one query that fetch the entity IDs, and only the entity IDs, not the associated values that we are querying. And that query uses the allow filtering option. And as we'll see next, this is very bad. After that first query, we have to run one additional query for each entity ID for which we want to fetch a value. So if we have 1,000 entity IDs for which we want to fetch values, then we have to run 1,000 queries to fetch these values. That's very inefficient. We thought about updating that data model or optimizing it, but its current definition makes it hard to optimize by improving the primary key definitions or adding indexes. So we went another way. Quick word on the allow filtering operations. This is bad. This is from the ScyllaDB monitoring tool. This is specifically graphing the number of SQL operations reading data with the allow filtering option. And as you can see on the left, there is this gauge that is at 90%. That means that 90% of the rows that are read via these queries are just discarded. This is just data that we don't need. So we only need 10% of that. So as you can guess, this is very inefficient. Okay, hopefully I've convinced you that relational features are great, but their implementation is bad. Let's now take a look at list features. List features is a new kind of feature that we've added recently. And the goal is, in a sense, to have a better cross-entity relation feature in the feature store. So that the goal is to replace the relational features in the feature store. So what is it? What we are calling a list feature has all other features is defined by its associated entity type, its name, and an optional version. That's exactly like other features. What we are calling a list is the value of a list feature for a given entity ID. So if previously we had a non-relational feature, which value would be like true or false, for a list feature, the value would be a list. So that's a collection of items. Each item holds a value and a timestamp. That's very much like what we are doing for relational features. So each item simply is a value, like an integer, a boolean, or whatever, and a timestamp for the timestamp of the associated event. We do have mandatory time to live metadata for the list feature. That's something that we'll dive into just a bit later. And one interesting thing is that the values, the item in a given list can be of various data types. We don't have to enforce that all the values of a given list must be of the same data type. This is completely open. Okay, let's take a look at a schema to make this a bit clearer. So at the bottom, we do see the list feature. Like on any other feature, this is associated with an entity type, feature version, and feature name. In addition to other features, it has a mandatory TTL. The entity type, like other features, is associated with the entity itself. Okay, and at the top, we see the list concept. So it is associated with a feature. It is associated with an entity ID, and it has a collection of values and timestamps. Let's take a look at a sample that hopefully will make this clearer. So let's imagine that we have a user.readingHistory list feature. So let's take a look at a sample list value for that list feature. So the entity is user. The name is reading history. Version not needed here. TTL 6 months. We keep an history of 6 months for your reading history, and after that we just drop data because we don't need that anymore. And the associated entity ID in this example is user1. And at the bottom, we can see the list of items for that list, which is a collection of values and timestamps. The value would be here the ID of the stories that you read, and the timestamp would be the date at which you read a given story. And as you can see, we can have multiple values, the same value, sorry, multiple items with the same value, like for instance, story A here. We will see later that we can also have multiple items with the same timestamp. Okay, let's take a quick look at the list operations that we want to support. We have a set of operations. The first 4 are really metadata operation. We want to be able, obviously, to create a list feature and to delete a list feature. That's something that we are not doing very frequently. Because of some automation, we are expecting to do that like once a day or something like that. For list feature version, that's the same kind of thing. We have to create them and to delete them explicitly. For this, we do have a bit more expected rate, but it's still very low, at like a few tens per day. Okay. Next, in terms of frequency, in terms of call rate, we have the remove list items with value. That's a very specific operation. And the idea, for instance, is that you should be able, as a medium user, to remove one given story from your reading history because you don't want that story to impact your recommendations. So that would mean that we want to remove all the items within a given list, so the list of your reading history, or remove all the items that have a given story ID with the value. This, we expected that to be called at a rate of between 1,000 to 10K operation per second. Next, we have the add list items. We're starting to talk a huge, significant rate. Add list items is just, well, as the name entails, adding an item or multiple items to a given list. This is a very frequent operation. This is like whenever a story is read, whenever a story is presented. Presented means the thumbnail is shown to you. So if you open the Medium homepage and we show 4 story thumbnails to you, then that's presentations, and this will be recorded within the feature store. So given the load of the Medium product, the user surfaces, we do have very high expected call rate for that. And even more than this, the get list items, and the S here is important, get list items, we typically want to be able to query the list of items in a given list that match a given set of constraints. The constraints being we want items that are no older than a given age, and we want also to be able to limit the number of items that are being returned. Apart from that, this is just returning all the items in reverse chronological order that match your query. The get list items, we have expected call rates that are very high, up to 1 million operations per second. So the add list items and even more the get list items operation really are the reasons why we need an efficient data store for storing the data for lists. And we'll see right after that how we did implement that. Okay, the next operation, remove all list items. We do know that we need to be able to clear your reading history. So that means just deleting all the items within the list that stores your reading history. The call rate today is unknown because we haven't yet implemented that. So we do expect that to be relatively rare, but as we'll see, we do have an implementation that makes it able to support very high call rate anyway. Okay, so efficiency, that's the key here. We want to be efficient, we want to be scalable. How did we do that? So let's take a look at the ScyllaDB data model. Goals and requirements. Just like we've seen, we need the implementation to be efficient and scalable. We don't want the latencies to start dropping because we are seeing more operations, more users using the product. That would be bad. So we want to be very scalable in that way. Efficient also very important because we are requesting the feature store and the list features at a significant call rate. As I've mentioned previously, one key also constraint regarding the data model is to be able to support having multiple items with the same timestamp in a given list, but with distinct values. That, for instance, means that this is super important, for instance, when we present multiple stories to you, just like I mentioned before. This will result in multiple post.presented story, post.presented events being sent. All of these events will have typically the same timestamp, but distinct story IDs. So this will create items in your presentation history list that will all have the same timestamp but distinct values. So that's why it was super important to add this requirement. Okay, so these were the goals and requirements. How did we do that for good? So this is the list items table, its schema. This is the one big table that does it all for lists. It stores all the list items for all the list features that are managed by the feature store. It has a pretty simple schema, actually, and we'll go over it right now. Okay, feature key. The feature key column is identifying the list feature. It is the result of the concatenation of the entity type plus the feature name and, if present, the feature version. That's so all the list that are corresponding to a given feature will have the same feature key. Next, we have the entity IDs. That's the ID of the entity a given list is associated to. So that would mean, for instance, user 123 for the reading history of this user. Next, we have the item key column. The item key identifies the item itself in the list. So it's the concatenation of the timestamp of the item plus a hash of the value. We'll go over it next. The value, that's just an opaque byte representation of the list item value. The feature store data model actually doesn't care about what is stored in the value. This is marshaled and unmarshaled by upper layers. But from the point of view of the data model, it doesn't really make sense what we are storing. We don't operate, we don't have operations that operate on the value. Okay, so that's the column. Let's take a look at the primary key. The primary key is a composite primary key. That means that it has both a partition key and a clustering key. And we've designed this with the help of the ScyllaDB solutions architect in a way that makes it efficient. So the partition key is made of the feature key and entity columns. What this means is that all the items of a given list, so for instance, the reading history of user 123, all of these items are stored in the same partition. This is one of the fundamental decisions that we made that provide efficient operations. The clustering key is the item key column. Clustering key, that means that all the items in a list are stored following the order of their timestamp. That matches the query that we're running on list. For which we want typically to retrieve the items in the list in chronological order. Using the item key, if you remember, the item key is made of both the timestamp and a hash of the value, means that we can have distinct items with the list with the same timestamp as long as they have different values, because the timestamp part of the item key will be the same, but the hash part, the hash value part of the key will be different. So that means that we have distinct primary keys for these distinct items. Okay. Clustering order, that's an optimization. Typically, not typically, but only, we do fetch list items in reverse chronological order. So here we are telling ScyllaDB that this is the default order that we will be using, and that allows ScyllaDB to perform some optimizations that will mean that fetching the items in reverse chronological order will be faster thanks to that. And next, the time to live. We set a default time to live on the table, and we also make sure that whenever an item is inserted, a row is inserted in the table, it also has an associated time to live. The time to live of a row is equal to the timestamp of the item that is being inserted, plus to which we add the time to live, so the duration of the list feature. So for instance, if the TTL of the user.reading history list is 6 months, if an item is added right now, its TTL value will be set to right now plus 6 months. And the nice part of it is that ScyllaDB will automatically delete the rows that have an expired TTL. We don't have anything to do regarding that. We don't have any logic to add into the implementation. Any row for which the TTL is expired will be considered deleted by ScyllaDB. So that's super useful for controlling our storage and usage costs. So here in this graph, we are showing the life cycle of a given list feature. So the red line corresponds to the number of items that are being inserted. That's the rate of items being inserted in the list. So at some point, the feature is created. So we are inserting items. We have a somewhat constant rate of insertions. And at some point, the list feature itself is deleted. We don't need it anymore. If we didn't have a TTL on rows, we would keep on adding items / rows to the table, which means that the storage consumption will increase and the cost would also increase correspondingly. Really relying on the TTL means that when an item is inserted, once its TTL has expired, ScyllaDB automatically deletes it, which means that we have a cap that's the blue line, we have a cap on the storage needs for the table. For a somewhat constant rate of insertion, we will end up having a somewhat constant storage usage for the table. And at some point, when the list feature is deleted, we will see the items being automatically deleted by ScyllaDB. And after the duration of the list features TTL, then the table won't have any data anymore for that list feature. So that's super important for us because that means that we do control our costs automatically. We don't have anything to do. Okay, that's it for the data model. Let's now take a look at how we implemented each of the list operations. Okay, we won't take a look at the metadata related operations because there is not much to talk about in terms of efficiency here. But let's dive right now into the add list items operation. This is a conceptually very simple operation. We have a bunch of items to add to a list, and we want to run the query on ScyllaDB that will just add that. In order to do that, we are simply running a batch operation made of insert statements. So in the code that is shown, the items that are the placeholder that are highlighted in yellow corresponds to the input arguments of the operation. So here, for each item in the set of items that we want to add, we perform an insert operation. So as we mentioned, we do have the feature T column, which is made of a concatenation of the entity type, the feature name, and the feature version. We do have the entity ID of the item. We do have the item key. So the item key is the concatenation of the timestamp and the hash of the value. And we have the value itself. And that's pretty much it. We make sure that we specify a TTL, the TTL of each inserted row, which, as mentioned before, is equal to the timestamp plus the TTL. And as TTL on ScyllaDB is stored as a duration, we just subtract the current time so that we have the duration after which the row will be considered obsolete. And then we just run the batch. By default, ScyllaDB will run this as a logged batch. Logged batch ensures that the whole batch operation will either succeed or fail completely. So that means that the insertion of all the items is atomic. Okay, let's illustrate this with a schema. At the top, we have the list item table partition before the insertion. And at the bottom, we have the partition after the insertion. So we do see that we have a couple of existing items on the user story read list for user A, for the user A entity. And we are just adding a bunch of items, and as the items have a more recent timestamp, they are all added at the top. That's the typical use case because items are typically added with the timestamp that is approximately the current time. So that means that we are only adding at the top of the table conceptually. Okay. That's the add list items operation. Let's take a look at the other super important operation, the get list items one. So the get list items, it's not mentioned here, but you have as input argument the feature and the feature, so that the feature name, the feature version, and the entity type. In addition to that, we have an entity ID. You want to fetch the reading history for a given user. So that would be user 123, for instance. And you specify also a minimum timestamp. You want to fetch the reading history for the last 1 month, for instance. We don't always use the whole 6 months of reading history. That really depends on the machine learning model that we are using, sorry. And we do have a limit. We typically make sure that we don't want to fetch more than like 10K items from the list, because that wouldn't make sense to fetch more than this. Okay, this is implemented with a very simple select operation. That's pretty straightforward. We just want to select the value and the item key from the fetch row. Obviously, we read that from the list items table. The where clause is pretty much what we expect it to be. We fetch on the feature key, we fetch on the entity ID. We use the item key sort structure so that we fetch the items that have that are older than the minimum timestamp. So that is just a lexicographical comparison thanks to the structure of the item key column values. We order them by item key descending, because that will mean that we will have them in reverse chronological order, and we specify the limit. Some notes. First bullet point 1. We run the query on a single partition. That's the maximum efficiency that we can have. Bullet 2, as mentioned, we discard all items. And 3, we rely on the clustering order and the clustering key for efficient sorting. Okay, pretty much it. Get list items. Let's take a look at a sample. So at the top, we have the list items table partition and all the rows for the user A. Whoops, I think I got this wrong. Yeah, no, that's right. Okay, we have all the rows for the user A entity. So that's what we are doing. And we do have a get list items call with some parameters. So obviously for the user A entity ID and the story rate feature. And we have a min type sum for 444 and a limit of 2. So we will drop items from the content of the table because of these two constraints, the min timestamp and the limit, and we will return the rows for the story that match the constraints. Very straightforward. Okay. Remove list items with the value. If you remember previously, I mentioned this as a kind of specific operations that we need on the list. Like for instance, when you want to remove one specific story from your reading history. So unfortunately, this is the one operation that we weren't able to implement with a single operation. We had to do a couple, two operations very specifically. The first operation is a select statement that we run in order to fetch the keys, the item key values of the items that we want to delete. So that's a very simple select. We just specify the feature key, the entity ID, and the value. Then once we have the item keys, we just run a batch of delete statements for each of these items. So if you know a bit about ScyllaDB, you might see that running the select clause on the value attribute typically would not be possible because value is not part of the primary key and there is no index on the value attribute. Well, actually, there is an index. I lied. This is an index that is made especially for that operation. It is called list items by value. So that's an index on the feature key and entity columns and the value ones. It is specifically added for the remove list items with value operation because we need to be able to query on the value. It is a local index. A local index means that the data for that index is stored on the same node as the base table. That's not always possible, but when that's possible, that means that the operation on that index will be faster than a global secondary index, which doesn't store the data for the index on the same node as the base table. Here, using an index is really faster than a scan because the query is highly selective. We have very few items in a given list that have the same values compared to the total number of items in a list. And thanks to the current structure, using a local secondary index is faster than a global index. Let's take a look at what this means in practice. So let's have, once again, the original table partition at the top. We want to delete all the items which have a value set to story C. So thanks to the local secondary index, we do identify the two rows that have the value story C. That's the first part of the operation. Then we run a bunch of delete statements. So that's 2 delete statements here using the item keys of the fetch rows. And as a result, obviously, the rows are deleted from the list. Pretty much straightforward. Okay. The last operation that we need to go over is the remove all list items. Very straightforward, actually. Thanks to the fact that we are storing all the items for a given list on the same partition, we can just drop the partition actually. So that's very straightforward. We just run a delete statement and we specify the feature key and the entity ID. So that's the partition key of the items that we want to delete. And ScyllaDB does its magic, and it just deletes all the rows for that partition, which means that it deletes all the items for the given list. And a bonus point, it's atomic. It's either completing successfully or not changing anything at all. Let's take a quick look at an example. It should be straightforward. Once again, at the top, the table partition before. We run a remove all list items operation, and unsurprisingly, we don't have anything left after that in the partition. And that concludes the implementation of the operation on top of ScyllaDB. Let's now take a look at some metrics for this implementation. One interesting part is that we have implemented the list operations on top of both ScyllaDB and DynamoDB. Part of it was to be able to compare the two databases. Conceptually, they are very close. They have significant differences in how they operate, and we really wanted to have a benchmark to be able to compare them using actual production data. So add list items, that's the first metric that we'll be looking at. So on these graphs, we are seeing the P50, P95, and P99 latencies for the add list items operation on both ScyllaDB and DynamoDB. Don't know if you can guess, but the blue line is DynamoDB and the purple line is ScyllaDB. What we do see is that the P50 latencies are very, very, very good. ScyllaDB is extremely fast at less than 1.5 milliseconds for the P50 latency. DynamoDB is also extremely fast, not as fast as ScyllaDB, but extremely fast at sub 5 millisecond latency. Things start to get interesting at the P95 and even more at the P99 latencies. Where ScyllaDB remains relatively stable, we are around, I don't know, maybe 2 or 3 milliseconds at the P95, and the delta between the min and the max is very low. We are seeing first higher latencies for DynamoDB, and also, very importantly, it's very less stable. We can see that for P95, it goes from between 13 milliseconds up to 35. And for the P99 latencies, it's from 40 milliseconds to 130. That's quite a significant difference. Let's take a look now at the get list items latencies. Same here, we are showing the P50, P95, and P99 latencies for all this for this operation. At P50, excellent. ScyllaDB is at 1 millisecond of P50 latency. That's excellent. DynamoDB is also very good at around 3.5 milliseconds, and both of them relatively stable. As for the add list items operation, things starts to get a bit worse, and maybe even significantly worse at the P95 and P99 latencies. So ScyllaDB remains relatively stable at around 5-6 milliseconds, maybe for the P95, and around 30 milliseconds for the P99, and somewhat stable, at least compared to DynamoDB, which is showing latencies of between 30 milliseconds up to 60 plus milliseconds for P95, and P99 is everywhere from 70 up to 230 milliseconds. So that's very interesting. What we get out of that is that ScyllaDB is very stable, strong performances, and predictable performances, better than ScyllaDB. One thing to keep in mind, though, is that we haven't yet added a caching layer on top of the DynamoDB table that we are using. So like a DAX cluster, for instance. We do expect that to have a significant impact, bonus impact in terms of performances for DynamoDB because of the high cache hit rate that we are seeing on the list. But we don't have the data yet, so we cannot compare them. Okay, thanks for making it this far. Let's have a quick recap of what we've seen. So, if you have a suboptimal data model, you will have queries that are slow, that will scale badly, and most likely you won't be able to optimize that data model. You will have to define a new data model that will be better. So take time to think about your data model before you start the implementation, because once you have production data using your suboptimal data model, it's too late. You will have to change it. We've designed the list features as a replacement for the suboptimally designed relational features. And I want to say thanks to ScyllaDB, who were of great help with that, showing us the ropes on some subtle behaviors that were important for our data model. So yes, thanks to you. When you want to design an efficient data model, the primary key is obviously very important. That's the fundamental decisions that you will make that will allow your data model to be efficient and scalable. Using indexes properly is also super important. And there are significant differences between local secondary indexes and global secondary indexes. So take time to understand this difference and to determine which is better for your use case. And last but not least, ScyllaDB is very fast, has very predictable performance, and that's super important for us. Yes, okay, awesome, thank you. We will now open the Q&A.
So much, Andreas. So we do have some questions asked, and I'll read them for you. So first, in an item key, you're combining a timestamp and a MD5 hash of a value. They'll support different values at identical timestamps, so have multiple values within the same timestamp. Have you observed collisions on MD5 hashes or any unexpected behavior, such as ordering or duplication, for that matter?
No, we don't. We do have specific metrics for that. So if this were to occur, we would likely be aware of it. The thing is, the values that we are storing are sufficiently distinct, especially when you add the timestamp into the equation, so that we don't have this kind of problem. Typically, as I mentioned, we are using this for use cases like presenting multiple stories to you at the same time. So the timestamp will be the same, but in these cases, the story IDs will be different because we won't be presenting the same story to you within the same surface at the same time. So that's really something that we thought about. And as of today, there are no collisions that we are aware of in our list data.
Amazing, amazing. Thank you. So let me pick up another one. So how easily does this model support adding new features compared to what previous models you were using before?
I would say it's not necessarily that it's easier to add features, because I think it's as easy as what we had previously with relational features. But the key difference is that we were aware of the fact that relational features behaved in an inefficient way. So we were typically restraining ourselves from using them. So this new data model that is efficient, that is scalable, has opened actually a lot of new use cases and refactoring for existing relational features that previously had to be postponed because we didn't have a proper we didn't have proper support for them in the feature store. So it's not really that it's easier. It's more like it was not efficient previously, so we just didn't do it. Yeah.
Great. Okay. I think we do have time for one more. So does TTLing data, as you currently specify, satisfy your data growth control, or how will you change it to store more data if needed?
Yeah, that's a great question. TTLing, I think, really does satisfy our growth. The key thing is that it's a lever that we have, and we can just adjust the TTL depending on our needs. So if, for instance, we create a new feature with a 3 months TTL, and we end up understanding that it's either too low, we would have to store it to store more data. Then it's just a matter of making sure that we do have the capacity of storing that new data and that the cost will be acceptable. So if that's the case, then it's just a matter of updating the configuration of the list feature and just setting the TTL to a longer duration. And if on the other end, we started with, let's say, 1 year TTL, and we do understand after the fact that it's too much because we are storing too much data, it's costing too much, and we don't actually need that data, then it's very much the same. We just have to adjust the duration of the TTL for the list feature, and automatically we will reclaim the space. So that's a very powerful lever that we have at our disposal, in addition to the way we dimension our ScyllaDB clusters so that we can keep the cost and the storage usage under control.
Amazing. Okay, thank you so much for answering the questions. Whichever questions we were able to tackle during the Q&A or through the chat will be answered over email after the event is done. So thank you so much. Andreas, any final words?
Not really. I was super happy to do that. I hope this was helpful for the viewers. I hope that you got interesting key facts, interesting data points from that. And yes, thanks for the opportunity to have me here.
Amazing. We're so happy to have you, and I'm sure the audience learned a lot with all your coverage for your story. Thank you so much. And before we wrap up, we'd like to invite you to keep on learning and exploring ScyllaDB. ScyllaDB xCloud allows you to fastly scale a cluster, be very efficient with flex credit and lowest cost possible as workloads scale to tackle a variety of curves of workload patterns. So make sure that you check ScyllaDB xCloud out. And we also invite you to the masterclass on latency and building and latency applications, low latency applications, sorry, and that will be taking place on September 25th. It's on from 8 a.m. to 10 a.m. Pacific time, and you can easily find and subscribe within the ScyllaDB.com/events. And we highly recommend you to be part of it. And last but not least, we also invite you to P99Conf, our All Things Performance Conference, really bringing a majority of use cases that are really focused on high performance, high throughput, low latency, and actually shaving all those performance aspects of current, critical applications. They'll take place on October 22nd and 23rd, and we invite you to subscribe and take place in this amazing and free conference. And thank you so much for joining us today.